Hi everyone, this is Sally Quast back again for lecture 3 on chapter 3 for the introductory chemistry uh, concepts in critical thinking, 7th edition by Charles Corwin, and it is for an introductory chemistry course. So we're now on lecture 3, which is going to cover chemical formulas, chemical and physical properties, physical and chemical changes, and the law of conservation of both mass and energy. So that's our topic. That finishes up the lecture for chapter 3. And then there's a homework assignment on this chapter, and I have broken it up in the 3 lectures into 3 sections in which you should do the Mastering Chemistry homework after each section. So let us begin. So we're going to look at chemical formulas. So chemical formulas they're formulas composed of 2 or more non-metal atoms in a molecule. That's one way to do it. Another way to say is that whenever you have 2 or more atoms together, that makes a molecule. If you have different atoms, then you have a compound. All right. So if you have the same atoms, it would be an element, but if you have different atoms, it would be a compound. Then a chemical formula is an expression of the number of atoms in each compound. There's a little typo there. So a chemical formula is how you represent the elements that are in each compound. So if you look at this, we have this molecule here. This is H2SO4, and in this molecule the yellow is sulfur, the white are hydrogens, and the red are oxygen. So that's pretty much in these molecules. The white are hydrogen, the red are oxygen, and then the yellow is sulfur. So the chemical formula for this is H2SO4, and it's called sulfuric acid. And sulfuric acid is the #1 produced acid in the country. We use more sulfuric acid than we use of any other acid. It's used a lot it's used in paper, making newspaper. They use it in making newspaper. That was one of its main uses. When you write a chemical formula, you have the symbol for the element. We talked about that in the last lecture. So that's H is hydrogen. You have 2 atoms of hydrogen. Then you have 1 atom of sulfur. So if there's no subscript number there, you understand it to be 1. And then you have O is oxygen. You have 4 atoms of oxygen. So you can see the importance of what I talked about the last time, memorizing those common symbols with their correct symbol and their correct spelling for their name. So this represents a chemical formula. This here is a compound. Okay, that represents a compound, and it contains those atoms. And so it's a unit. This whole thing here is called a molecule. And if you have H2SO4, there's only one compound it can be is sulfuric acid. That's the only thing it can be. So this identifies the particular compound. Now, writing chemical formulas, the number of each type of atom in a molecule is indicated with a subscript in a chemical formula. If there's only one atom of a certain type, then you don't have to put a 1. Okay, you just put the symbol. So a molecule of vitamin B has 6 carbon atoms, 6 hydrogen atoms, 2 nitrogen atoms, and 1 oxygen atom. What is the chemical formula? So you write them down the way you're given. So it says carbon first, so you write down carbon. It says 6, so you put a subscript 6. Then you have, next one is hydrogen. There are 6 of those. Okay. Then you have 2 nitrogen. N is nitrogen. You put 2. And you have 1 oxygen, so you put O. You don't have to put a 1 there. So this is called a chemical formula. It's the way chemists represent compounds. We represent compounds using chemical formulas. Interpreting chemical formulas. So some chemical formulas use parentheses to clarify atomic composition. Ethylene glycol, a component of some antifreezes, has a chemical formula of C2H4, and then it has parentheses OH2. We do that in chemistry to show you that these 2 atoms are stuck together. They're bonded together, and you have 2 of them. So you would look at this, and you have 2 carbon atoms. Now you have 4 hydrogen atoms here, but see this 2 here? That applies to the O, and it also applies to the H. So that gives you 2 hydrogens here, plus the 4 you have here will give you 6. And then it gives you 2 oxygen, so that means you'll have 2 oxygen atoms. You could say you have 2 OH units, all right, and then break it down. So the total number of atoms you have would be 2 carbon, you'd have 6 hydrogen, so that'd be 8, and then you have 2 oxygen, So then the total number of atoms that ethylene glycol would have would be 10. So that's one of the things on the test. You have to be able to give the number of atoms of each of the elements, and then you'd have to be able to give the total number of atoms of the compound. Now this here is a law, natural law about matter, and it's called the law of definite composition. And what it says is that if you have a compound, they always contain the same elements in a constant proportion by mass. Now what does that mean? Well, what that means is if you have water, and wherever you take a sample of water around the world, you will find by weight it would have 11.2% hydrogen by weight and 88.8% oxygen by mass or weight. No matter where you get it from. If you make it in the lab, if you make water in the lab, you'll have it. If you find it in the ocean, you'll have it. So it doesn't make any difference where you get it. It's going to have that. It's going to have that composition. If you go back to this other one and you weighed this here, the definite composition, this would tell you that ethylene glycol would always have, 2 atoms of carbon and 6 hydrogen atoms and 2 oxygen atoms by mass, okay, by mass. So this is by the weight. So that's important, because that means if you take a compound and you analyze it and it has a certain percentage by mass, then that's a way to identify it. And that's one of the ways that we can identify the atoms or the elements that are present in compounds. All right, now we're on to a new topic. Okay, this new topic has to do with properties. We have physical and chemical properties. So another way to organize matter is by physical and chemical properties. Okay, that's another way. So a physical property is a characteristic of a pure substance. And remember, pure substances are, see if you can guess, elements and compounds, okay? Not mixtures, all right? So a physical property is a characteristic of a pure substance that we can observe without changing its composition. Physical properties include appearance, melting point, boiling point, density, which we've done some work on density, heat, electrical conductivity, we haven't really done anything on that yet, solubility, and physical state. So anything that you could describe could be color, texture, any of the properties that you can describe without changing the nature of it. That's called a physical property. A chemical property of a pure substance describes its chemical reactions with other substances. And that's really another way I like to say it is a chemical property is how matter interacts with other matter. Gasoline in your car interacts with oxygen in the air to burn, to produce light and heat and energy. So that's a chemical property of gasoline. All right, that it combines with air to produce carbon dioxide and water plus heat and light. That's a chemical property. A physical property of gasoline would be that it's a liquid, it has an odor, has a certain density, but it doesn't have solubility, it doesn't have any solubility, so they would be physical properties. Chemical properties tell you how matter interacts with other matter. So here we have a chemical property here. This is a great example. So you have sodium metal over here, and sodium metal is a very, very reactive metal. If you put sodium metal in water, it will explode. And then you're going to react it with chlorine gas, and chlorine gas here is a poisonous gas. It's a greenish color poisonous gas. They used it in chemical warfare. During World War II they used it. I'm not sure if they're using it today. And when you combine these two together, okay, you get a new substance which we all know is table salt. And table salt is used for preserving things and for enhancing flavor. So here you have this, here's the atomic of the atoms of sodium, and then here's the chlorine. Chlorine actually exists as a molecule, 2 atoms together. And you put these together chemically and you get this white, you put these two together and you get this white solid that we put on our food for flavor, and we use it to preserve. And this is how the sodium chloride looks like. It's a crystal. It looks like this down here at the bottom. So that's a chemical property. So the chemical property is that sodium reacts with chlorine to produce sodium chloride. Or you could say this, the chemical property of chlorine is it reacts with sodium to produce a totally new substance that has new properties. If you go back to those other ones where we talked about physical properties, density doesn't change the nature of your substance. You still have, you were getting the density of different things in lab, you're getting the density. It doesn't change the nature of the water that you got the density, or the piece of metal that you got the density. All right, now we're on to changes. So we just did physical and chemical properties. Now we're going to talk about physical and chemical changes. Again, these are all ways to organize matter. So what we're doing here is organizing matter. So another way to do it is physical change. So a physical change is a change where the chemical composition of the sample does not change. It most commonly includes the change of state. Okay, that it's the change of state, going from a solid liquid to a gas. That's the most common example that we have of a physical change. You could also say chopping something up, pulverizing it. That would be a physical change. But generally in chemistry, we speak about physical change as a change from the solid state to the liquid state to the gas state. A chemical change is a chemical reaction. That's what happens. The composition of the sample changes during a chemical change. If you go back to that sodium and chlorine one that we had, when you put sodium is a shiny metal and chlorine is a poisonous gas, and you put them together, you get a white solid. Totally different. Okay, it looks different, different properties. It's all different. All right, so that would be a chemical change. So here's evidence. Here's some evidence for a chemical change that we have. One is bubbles. That's usually a gas being formed. Okay, that's one way for chemical change. Another one would be light or release of heat. All right, that would be another. If you had light, like this looks a little bit like sodium and water. All right, so that would be light and heat given off. And then we have this one here. We have a solid being formed. This is called a precipitate. You put two liquids together and you get a solid. That's another evidence of a chemical change. All right, so heat being absorbed or released, bubbles, and then if you put two solutions together and you get a solid being formed, that would also be another example of a chemical change. All right, so another thing we have is a conservation of mass. We're going to look at the laws of conservation here. So Antoine Lavoisier, he is really in a lot of ways French and did a lot of the measurements, found that the mass of reactants before a chemical change was always equal to the mass of products after a chemical change. That's very, very important. That's a natural law. That the law, if you start out with 20 grams of a substance, no matter what you do with it, whatever you get that you form, it has to weigh 20 grams. Mass has to be 20 grams. So the law of conservation of mass states matter is neither created nor destroyed in a chemical reaction, only changed in form. But the amount, if you were to weigh it on a balance before and after, there's no change. There should be no change in mass. Now there is change in mass sometimes because you spill things or you don't react them completely. But if you are very careful, and we do experiments that show that, you can actually show that the mass of the reactants, what you start with, is equal to the mass of what you end up with. So here's an example, and this is just a simple example. If you took 1 gram of hydrogen, combine it with 8 grams of oxygen, you would get 9 grams of water. All right, they would add up. And then if you had 3 grams of hydrogen with 24 grams of oxygen, you would get 27 grams of water. So if you had 50 grams of water break down to produce 45 grams of oxygen, how many grams of hydrogen are produced? So you have 50 grams, you had 45 grams of oxygen, so you subtract that and you'd have to have 5 grams of hydrogen. They have to add up. That's what this law says. This is a natural law. It's not a theory. It's a natural law that says the matter that you start out with, you have to account for it.